right, let's get started again. Everybody come on in, get sat back down. So I was encouraged to make some potato jokes. You guys want to do a couple potato jokes really quick? Tawny says yes. I'm blaming you. Yeah. Well, yeah. You may wonder why they asked me to MC, but I promise it's going to be spudtacular. Okay, like one person laughed. What did you expect? Well, I don't know. There's so many potato jokes out there. I just don't know where to start. And maybe we should just end there. All right, so with that, let's go ahead and get rolling with our next presenter. Some say that he can work magic, that he really can work magic, and that he can demodulate 802.11 frames with nothing but a deck of cards. All we know is his name is Peter Mackenzie.
Good morning. That was a bit. Good morning. Thank you. I wonder, as Wi-Fi engineers, what you think when you hear the term IoT, Internet of Things. From chatting to a lot of Wi-Fi engineers, sometimes I think you think of it as a problem. You know, if we're being honest, if this bus load of devices that have shown up that all want connectivity to our network could just magically disappear, it'd make our lives a lot easier. Yeah? Especially when we think about a lot of those devices being 2.4 gigahertz only, and we have to think about how we're going to handle them, and it just causes us problems. But I think when we're thinking about IoT, from our sort of Wi-Fi perspective, we miss the bigger picture. And we miss the opportunities that this incredibly fast-growing industry, I think, provide for Wi-Fi engineers. And I want to, my journey, I guess, into this started with a phone call from one of my wireless LAN design customers. It's a large UK university. And they phoned me up and they said, oh, as well as doing Wi-Fi design, can you do RF design for a Thread lighting system? Now, at the time, I knew very little about Thread. I knew it was based on the 802.15.4 standard, and I knew it was 2.4 gig. So I said, yeah, sure, we design 802.15 Thread lighting systems, of course we do. Thinking to myself, how hard can that be? Well, the rest of my talk is going to be sharing with you the journey that those few words led me on. Some of the lessons I've learned, but also I want to share with you what I think the potential opportunities are for everyone here, for people who are Wi-Fi engineers in this incredibly fast-growing industry, which desperately needs the tools and skills which I think we have in our industry. So I want you not to think of IoT as a problem anymore, but as an opportunity. And I think it provides a great opportunity for many people in this room. So let me talk to you a little bit about this project, which I was asked to do. It was a university building. Here is the building. It was a science laboratory building where they did loads of sort of laboratory testing. Some of it was apparently top secret, so I needed escorting into the certain labs. But this was the building. I obviously got some ground plans for the building. This is just a section of some of the buildings. You'll notice on these plans, there's lots of colored squares and rectangles. The yellow lines are like strip lights, which are going to be installed in the buildings. You've got purple squares, blue squares. They all represent different lighting fixtures within the building. And in each side, each of these lighting fixtures was going to be a Thread wireless communication module installed. And it was this Thread system that they wanted me to help design. So I was thinking, okay, I need to learn something about Fred if we're going to design a system to use it. So I started with the 802.15.4 standard, and I want to just talk a little bit about that standard with you before we go any further into this project. 15.4 is a standard for low-rate wireless networks, and it's designed for low data rates as it designs. It's also designed for ultra-low power, ultra sort of cost-effective, low complexity, low data rate wireless communications. That's really what the standard set out to do. That was the purpose of the standard. So what does it define? Well, it defines a MAC and physical layer for these technologies. It actually defines 3 different frequency bands. The one that I was most interested in was a 2.4 gig, and that's what we're going to talk about the most during this presentation. Now, when you look at the 15.4 standard, it's the basis for many, many different wireless specifications which have been built on top of it. There's Zigbee, there's RF4CE, there's ISA 100.11a, there's WirelessHART. There's many, many different specifications which have been built to work on top of 15.4. Most of them, like Zigbee, WirelessHART, they're for control, sensors, remote control networking. Not traditionally what I think people would class as IoT. But there's one particular interesting specification, which is the 6 low-pen specification, which does something which none of the others do. And that is, it adds IP version 6 on top of, as a network layer on top of 15.4. What that means is it can allow us to have these 15.4 devices directly addressable from the internet. And built on top of 6 low-pan is Fred. Fred sits above it. So Fred, from the outset, has been designed as an IoT technology. It's been designed so that it can connect devices with direct connection to the internet and the cloud. Fred allows up to 250 devices to be connected together in a wireless mesh, and then that mesh gets its network connectivity through something called a Fred border router. So when we look at the Fred system, we can see at the very base, as its physical and MAC layers, it's 802.15.4. Built on top of that, providing the networking layer, is 6 low-pan. And the IPv6 routing, which goes on top of that, allowing us to get network connectivity with it. And then it runs UDP built on top of that. It also has 128-bit AES security built into the standard as well. And then on top of that, people can run their applications, such as this lighting system, which I was asked to help design at the university. So that's a 15.4 standard and how Fred fits in. What about how it interplays with Wi-Fi if it runs on 2.4 gig? Well, as with Zigbee and Fred, there's some specified in the 15.4 standard. There's some channels which you can use in 2.4 gig. We have 16 different channels. Each channel is 2 megahertz wide, and there's 5 megahertz between the channels, between when one starts and one ends, or between center frequencies. If we want it to operate nicely with Wi-Fi systems, we've really got 4 channels we can use. The channels go from 11 to 26, and as you can see from the graphics, there's channel 15, which nicely fits between our Wi-Fi channel 1 and Wi-Fi channel 6. And then there's channel 20, which sits between channel 6 and 11. And then beyond channel 11, we have both channels 25 and 26. So if we limit ourselves to those 4 channels, we can actually interplay fairly well with traditional Wi-Fi. The system we were putting in at the university was going to be working on channel 26, which I think is the best channel if you can get away with just one channel, because it keeps it the furthest away from the university using 1, 6, and 11, so it's keeping it furthest away from their channel set. So, knowing a bit more about the technology behind it, I thought I'd really better understand its lighting system that we were meant to design for. So I decided to do a bit of Googling to find documentation. I thought I might be able to find out receiver sensitivity values, what signal strength do they need, how many hops can you have in a match, and this is pretty much the documentation I found. Everything from my day's research, this is what I found. So from this, I managed to realize that they have these little modules that connect to the lights called luminaires, wireless luminaires, and they have a thread radio module into them. These radio modules, which are up here, they connect to a low-powered access point, which they call a border router. And this is all thread communications that happen between them. And then that border router gives its access to the network, the internet, and there is a link server which provides the application traffic on top of it. That sort of left me with quite a lot of questions. What signal strength do the modules need? If I'm going to design for them, how many border routers do I need? How far away can a border router be from one of these modules before it can connect? I had a whole host of questions. Typically, in one of these scenarios, how many border routers do they put in? Do they let an entire building match together and have one border router? Or is it like one border router in each room? Nothing seemed to be on the internet to tell me. So I decided to speak to the engineers at the company themselves, who basically said, we don't really know, we just buy this thread module and put it in our lights, and it provides connectivity. So I said, well, how do you normally design for them? What tools do you use? What's a typical design? They said, oh, this is our first major installation. We don't really know. But it's okay because the university said they've got some really good RF engineers who do all the designs for them. Yeah, that's me. So I started thinking, well, there must be design tools in at least the 802.15 space. Whether it's Zigbee design tools, Thread design tools, there must be them. So along came a bit more research, and I wasn't really finding any. So I contacted this company again and said, can you send me some gear so at least I can maybe do some testing and find out how it works? So they agreed to send me some equipment. This is what I received. The little device on the left-hand side is a module that they put into the lights. It's a little thread radio. And then the one on the right-hand side is a border router. They also send me their application server as well to plug in. And they sent me 3 of these modules, and they said, turn it all on, and the little modules will just connect to the border router, and you'll know if they're connected if you can do an IP version 6 ping to them. So I turned it all on, and I could ping them. They were in my lab. So I was like, great. Can I get any information from them? And they said, what like? I said, maybe RSSI? Can I see what signal strength the luminaires? No, we can't get that. So I was a little bit feeling, I don't really know how can I can obviously take one of the modules away and see when I lose connection with the border router, but I won't know what signal strength I'm at. I won't know what RSSI value I'm at. It's going to be very difficult to design for this. So I started realizing as I did a lot of research, there was very, very little tools in this market. And we're really spoiled in the Wi-Fi market with Wi-Fi design tools, with heat mapping products, with sidekicks, with the amount of tools we have available to design networks. This is an industry that basically has nothing. And the people putting these radios into their products are just buying radios and putting them into their products. They know about lighting systems. They don't know about thread or how to design for it. So there was very limited tools. So what did I come up with? How was I going to solve this problem of how I was going to design a network? Now, what they basically wanted me to do, obviously the lighting fixtures are in a certain place, as you saw on the map. So the idea was I was going to design where these border routers were going to go. So how was I going to do that? Well, what tools did I eventually find? I managed to find some development adapters, 2.15 development adapters, which apparently would be able to give me RSSI, allow me to do packet capture, and allow me to start to see some of what was going on between its white box A and white box B. So that was at least a start. So I ordered one of these development adapters. One of my hopes from using these adapters was if I could at least measure some sort of protocol and connectivity between these devices. I was thinking, if there isn't a design tool out there for it, maybe I could come up with, calibrate 802.15 to 802.11. That was the theory anyway. So I was thinking if I could say, well, this is how far I have a border router, and this is how far I can get one of my luminaires to connect, what would that look like with an 802.11 2.4 gig 802.11b access point? Something that's going to be similar to the thread. And then I can design with Ekahau, let's say, a network using Wi-Fi, but calibrated to 802.15. So this was one of my ideas of how I was going to do the design. The other thing I discovered as I was going down this chat and chatting to people was that iBwave actually had in their cellular product, not in their Wi-Fi product, so in their enterprise product, they did actually have a Zigbee radio as one of the modules you could put in there. So they had the predictive models for a Zigbee radio. So I thought, well, that's potentially an option for designing this too. So it was basically, they were my three methods I came up with after doing a lot of research. So let's talk about the development adapters first of all. The first one was a Texas Instruments CCD bugger. This was the first one I found and got. And it did allow me to, at least from the border router, see the frames, see what RSSI I could pick them up at. My only problem with this was I was obviously seeing the RSSI that my development card saw and not what the actual luminaire little white modules were seeing, but at least it gave me something. And I found packet capture quite difficult with it though. And then I discovered something called the NPX Wireless Packet Sniffer, which I actually have here. It comes in a nice little case, so it's not just a board. And this thing was very easy to capture packets, capture signal strength. It could do BLE as well as 15.4. It could, and you could get all your decodes into Wireshark. So this sort of became my best friend in this project for a while. And it allowed me to at least do things like measure signal strength, so I could measure wall attenuation measurements, and I could start to do some of the sort of things we do in Wi-Fi design by having a card I could at least get data from the system. So talking about packet capture and 15.4, one thing I learned when I started looking into the protocol and at some captures, actually there's a lot of transferable skills if you know 802.11 protocol to 802.15.4 protocol. There's a lot of things which are familiar. So there's a lot of easy transferable skills. If we look at a 15.4 Mac frame format, it's got things that we're probably familiar with, like frame control. That's the first 2 bytes of the 802.11 Mac header. It's got sequence numbers. We know what sequence numbers are. It's got some addressing fields, source, destinations. It's got a couple of unusual things in there. It has a source and destination PAN address as well. But it's got security headers because it does encryption. It's got IEs. It's got a frame payload. It's got a frame check sequence. A lot of the same things we see in Wi-Fi headers, slightly different in how we interpret them, but were there in 802.15. When we look at the frame control, again, there's a lot of similar things. There's a frame type. Again, which we're used to with 802.11. In fact, if we look at the different frames, we've got beacon frames, data frames, acknowledgement frames. A lot of the same concepts which we understand are actually transferable. So I was more encouraged, having done a little bit of research into this. What about the calibrating? Could I calibrate 15.4 to Wi-Fi? That was going to be, what we did is we set a test up. We set the border router up, and I wanted to know how far I could go when one of these little modules lost connectivity. What was the limit? So we set a router up from my office, and we walked away. And we wanted to do it, first of all, in line of sight. So we set it up actually on the balcony, and we walked away, measuring the distance. And we got to a point, it was about 220 meters away, where we determined this was a less stable point where we could get all our pings. When we went beyond that, we started losing pings to the module. We then replaced the border router with a Wi-Fi AP. Because we decided to go for something that was BPSK, because we were trying to match the modulation and more closely off the border router. So when we had it just with 1 megabit data rates turned on a 2.4 gig AP. And we switched that to a wireless AP, and then we measured the RF signal strength at the same point that we could get to, and we got about neg 79 dBm. So I knew this system would work over that sort of distance. We'd also talked with the company and agreed with the university in the lighting system. We were going to allow for sort of 10 dB fade margin. So if I was going to design it with a tool like Akahau, I was really trying to get, from a Wi-Fi AP point of view, a neg 69 dB boundary. So that was my calibration. How would that actually play when you put it in an indoor environment with walls, and would it still work out? So when we went to site and I did my sort of AP on a stick survey, this is actually showing the green boundary here is the neg 79. So this is where it should work up to, not the fade margin boundary. So we can see from this that if my calibration's right, if I take one of the modules beyond where I've got green into the grey area, it should stop working and I should not be able to ping. The problem was when we did that, I got into the very top corner of here, I got up here, and actually my modules were working fine. No problem. So my calibration wasn't really working as I hoped it would. Then when we looked at modeling it in the IBWave software, this is what showed the coverage. Now I haven't shown the scale on here, but what was really interesting was it was showing that around here where my device still worked, I was actually getting around neg 75, 79 dB, which was in my bounds of what should work. When I went beyond that up here, it dropped to neg 80, and that's when my module stopped working. So I was really impressed, actually, with the predictive model that IBWave provided, because it actually seemed to be really matched the experience of taking these modules out into the environment. And it led me to believe that that was maybe my most accurate platform to do the design on. So that's how we decided to go with the design. It was just really fascinating just how accurate it was. Now, obviously, when we used, for the IBWave model, we had to put all the wall attenuation values in, and we used our development card. So we were actually measuring the loss of the 15.4 radio. And I think the reason the calibration didn't work is because we're obviously using a narrow beam width, we're only using 2 megahertz, it was somehow not attenuating as much through a wall as Wi-Fi was. And that was why the calibration wasn't working as accurately. So we did the design and we installed it. The next issue I guess I had for this design was how often do we put a border router? Because these lights can mesh together. And we tried, the one thing that the lighting company could tell us was they found if you get more than about 2 hops, it can start to break. So we were obviously trying to work out what was the best approach for how often to put a border router. What we ended up deciding to go with is actually to provide, using our 10 dB fade margin, actually just get like complete primary coverage with border routers. So that theoretically every light could connect directly to a border router. The theory being is that gives us some resilience. If one router fails, the devices can match and get to another border router. So we came up with that as our design specification. Quickly just pull up IBWeb. So this again is that same AP that I showed you in the design. Here's the area where it would work. But we did include what we classed as a sort of fade margin into that. So when we looked at the fade margin, that's now the darker area. That's really where we set our coverage boundary. And we designed so we could have basically primary coverage in every area to that level with border routers. And that was pretty much our design, and we came up with a full design which I'll quickly share with. So that was, we came up with a full design with border routers in different places. The system was installed, it worked, I'm pleased to say. We've not had any complaints yet, but that's a little bit about my journey into my first IoT design. I guess moving forward is where do we go from here as an industry? There's clearly a need for better tools in the IoT industry. You know, Wi-Fi design is just as much, solutions needs good Wi-Fi just as Wi-Fi does. And we need good design principles and good design tools, I think, if we're going to design good app for IoT. So, you know, I think there's a great opportunity as wireless engineers for us to take our skills and our tools into this industry. And actually, it's a massively fast-growing industry. I also think that, you know, this is my challenge to any vendors who are making tools out there. Start building this technology into the Wi-Fi tools and allow us to move into those industries. You know, at the moment, yes, there was something in IBWave, but it was in the main cellular tool, which is probably a price point beyond most Wi-Fi engineers. So it'd be great to see that come into the Wi-Fi version, and I think we need more tools to tackle this thing. But we also need to be educated in these systems as well. And I think that's great that CWNP this week held the first CWSA class. That's a great start, but let's get, as wireless engineers, educated in these other wireless technologies so we can take all these great principles of RF design we've got and move it into the IoT space. That is me done. Thank you very much.
Awesome. Thank you, Peter. Any questions or anything? We can get the text questions. Okay. I don't know if there's any text questions for you. Any verbal questions before we let Peter go? Yeah. Sorry, JD. Let me get the mic down to you. Should we let this guy ask questions?
Yeah, why not?
Okay.
Early night ones there.
I was just curious, were you able to find what SNR you needed and what noise floor was at 2 megahertz wide? Were you able to actually put numbers on that?
It's a great question. The only way, obviously, we did do some spectrum analysis just with our standard tools, so obviously that gave us an idea of the noise floor. In terms of SNR, I didn't actually find out, I could never find out an exact amount. It didn't seem to be, from my experience, it seemed to be much more reliable than Wi-Fi. So I would say it doesn't need to be as high. And I think that's why we could, it seemed to be that it just, when we tried to do that calibration to Wi-Fi, it didn't quite match. It was close. It wasn't a long way off, but it wasn't quite there. And it does seem to be a little bit more cope with a little bit less SNR than we typically need for Wi-Fi. But I haven't got a figure I could put on it, no.
Any other questions? All right, great. Oh, yep, one more. Hang on, one more.
how did you just determine how many little radios could go to a router? Or was that given to you by the manufacturer, or was that just testing that you performed?
Yeah, so the manufacturer understand there's a bit on that. They can cope up to the actual manufacturer, I think, could cope up to 200 connections per radio. So it was such a big number, it never really seemed to feel like a limitation on this one. It was a bit like AP radios with association. One of my concern was whether there was going to be an impact if you had too many. But actually, going with the model we did with that 10% sort of fade margin, and going with the sort of model we went with, it actually ended up being that, I think when I calculated, we were not going to have more than about 20 connections per border router anyway. So we were well down on that limit. It might be we over-specified a number of border routers, but the system seemed to work, and that was always my worry, whether we were putting in too many, but it seemed to work well. So.
Cool. I think we got time for one last question that was submitted by Tim. Were all the dissectors built into WirelessHART for 802.15.4 and Thread? Were those built in?
Yes. You had to get the right version of WirelessHART. I can't remember exactly which version it was I used now, but I know we had to install. It wasn't the latest version. I actually had to install an older version to get it to work, and I'm not too sure why that was the case.
So the dissectors were not included in the latest release of WirelessHART?
No, whether they've now been put into the latest, this was quite a number of months back, but at the time, they seemed to have been, they were in one version that seemed to get included out, and then I was told they were being put back in.
Gotcha.
I've not checked that.
A couple more really good questions I want to take some time for. I think this is a good one. Yeah. Why didn't they just hardwire the lights?
That's a great question. I don't really have a good answer to that question. It's obviously they were getting power to it, but for this control system, for whatever reason, I'm presuming that the university decided they wanted to go down this Thread approach. I'm guessing it's just that, there's a lot of light fittings. They already have power in the ceiling. I guess they would have to get data connections to every light. And that costs money, doesn't it, pull an Ethernet cable? So I'm guessing that's the reason. There was a lot of lights. There's a lot of Ethernet cable to pull. If you don't need to do it, why pull it? Absolutely.
Okay, and this really is the last question before we go to lunch. Is there a worry of denial of service attacks on the network?
So what I was told by this was that the system is controlled wirelessly via the Thread system, but it fails with the lights on. So if you did a denial of service, you wouldn't be left in the dark, you'd be left in the light.
Awesome. Well, thank you very much. Let's give it up for Peter Mackenzie. Thank you, Peter.